All right, the goal of this section, and really this chapter, is to take a polynomial and factor it, any polynomial, and find its zeros. Sometimes that's difficult, especially if we have a very big polynomial and it doesn't factor by grouping, or it's not a quadratic and we can factor it that way. And so we have a bunch of tools that we can use to determine what are possible zeros, or again, factors of the polynomial. This is one of them. This is called the rational zeros theorem. So if we have a polynomial, this is just the general form for a polynomial, p of x is a sub n x to the n plus a sub n minus 1 x to the n minus 1, and so on, all the way down to a1x plus a naught. Right now we already recognize some parts of this. We know that a sub n is the leading coefficient, a sub n x to the n is the leading term, n is the degree of the polynomial, and a naught is the constant term. Also tells us the location of the y-intercept. One thing about this polynomial that we're going to require for this theorem is that this polynomial have integer coefficients. So you won't see any fractions in their coefficients, although that's not a problem, or we could take care of that if it did. All right. If p over q, so this is just some number, a rational number. If this is first off, it's a rational number in lowest terms, and if this rational number is a 0 of p of x, then we know that the numerator in this fraction is a factor of the constant term, and the denominator is a factor of the leading coefficient. Right? So if we have a polynomial with integer coefficients, we can determine a list of all the possible rational zeros. They will be of the form p over q, where p is a factor of the constant term and q is a factor of the leading coefficient. All right, so I have a polynomial over here. P of x equals x cubed minus 7x minus 6, and we want to find all the possible rational zeros. All right, so first off, we look at this polynomial and we look at its coefficients. So the leading term here is x cubed, its coefficient is 1. That's an integer, it's good. Negative 7x, negative 7, also integer, and 6x, also an integer. So this is a polynomial with integer coefficients, which means it qualifies for the rational zeros theorem. All right, and so we know that any rational zeros of this polynomial will be of the form p over q, where p is a factor of the constant term. So let's list all the factors of the constant term. Constant term is negative 6. What factors of negative 6? Well, 1. So plus or minus 1 is a factor. 2, plus or minus 2. Both of those divide evenly into negative 6. Plus or minus 3. And of course, 6 itself. Okay. Let's list all the factors of the leading coefficient. Leading coefficient is 1, makes this very simple, just plus or minus 1. And now we construct all possible combinations of p over q. These are the possible rational zeros. So we'll take this over plus minus 1, 2 over plus minus 1, 3, and so on. You can see it's just going to be this list here. So plus minus 1, plus minus 2, plus minus 3, plus or minus 6. Okay, from here, we've taken the whole number line, all possible rational numbers it could be, and limited it down to a list of just 8. Right? So if this thing has rational zeros, it's going to be in this list. Right? And using synthetic division, we can quickly go through each one of these and determine whether those are zeros of this polynomial. We'll do that in the next video.